Let's plot the data. So we're gonna put colors into the class. I mean, in the scatter plot, we're gonna use color to differentiate between one class and the other. So we're gonna need an index to see what are the samples belonging to class 0 and also for 1, right? So we're gonna create it in this way. So basically we are looping over the training data, and in the case of the index 0 is only if the training data in the last column is equal to 0. That means that here we are capturing the index of the class 0 training points, and same thing for class 1. We could do this in a loop and use a dictionary for the index, but in this case it's simpler doing like this because it's just 2 components. If later we extend this for more components, will be more suitable to do it that way. So here we are scattering the data using the index we just built. Let's use size equal to 60 and the color equal to green. Okay, so we need to use a color map. To have the labeling in the plot. It's a bunch of color maps. You can find them in the way. Let's use that one called winter. And so the label is going to be class 0. And the same thing for the class 1 guys. Let's use blue and class 1. Let's use a legend with a location in the lower left, and let's show. Here we have a problem. Okay, here we go. So we can see this training set, right? Coming from 2 different Gaussians, and depending on the Gaussian, we use it as the class. So now we are ready to run our logistic regression model and feeding it into this training data. Okay, so now we're going to plot the surface of the just trained logistic regression to see if it makes sense with the training data. I pasted the code here because it's not part of the scope of this video to understand how to plot a surface, but you can pause the video and take a look I'm gonna basically fastly explain. Here I'm creating the domaining where the first variable lives, then the second variable. Here I'm using basically the granularity of the plot, or how um, precise I want it to be, the plot in terms of the 3D visualization. I mean, the thinner here, you're gonna get a more realistic 3D surface, but it's going to use more points. And then you need to do this mesh grid, okay, to understand that then you evaluate Z with the sigmoid function of X and I, but in this case, we're using the real betas, the ones we found after training the model. So then we create the surface with this function, then we set the limits, okay, and we end up doing the scatter plot in this loop here. Okay, so I'm gonna run this, and here we go. So this is the surface. As you can see, our logistic regression classifier, it is a sigmoid function here, and it is basically dividing the training points in the two groups. So if the training set is too hard, let's say that here there is a lot of overlap, then the logistic regression is not going to be able to divide them. Okay, so this is telling, the logistic regression tries to put in one side of the sigmoid the elements of one class, and in the other side the element of the other class. Keep in mind that basically the logistic regression is just trying to find, first of all, a line that divides both classes. Actually, if you look this plot from the upside, you're gonna see that in the middle of the sigmoid there is one line, and this model is going to work well as far as both classes can be separated by this line. And that line is actually the exponent in the part below the ratio in the sigmoid function, right? Recall that this is the sigmoid applied to a linear combination. The linear combination is exactly the line that divides both classes. And as far as that line divide them well, it's gonna be easier for the sigmoid later to live in the upper side one class and in the left downside the other. We can also extend this model to more than just two classes. For example, for a multi-class classification problem with k classes, we just run k binary logistic regressions, one for each of the classes taken as class 1. So each of those logistic regression will generate a solution like a vector of betas. So we're gonna have like k beta vectors, one for each of the classifiers. And later, the probability that a new data point belongs to class k is basically a generalization of the sigmoid function, as we can see in this equation. Also, we have to keep in mind that the logistic regression is a discriminated classifier. It means that it models directly the probability of the class given the data, but it cannot generate any synthetic data from the model because there is no any modeling directly on P of X. In future videos, we are going to cover the differences between discriminated and generative models.